case. We had a little bit of a technical snag with the usual stuff here, so let me actually try. As many of you probably noticed, I'm using Microsoft PowerPoint on the Mac. What's the problem? Okay, so what I'm going to do, we're going to split between me and Dimitri and Konstantin. We'll probably get in this order. I'm going to spend probably about 30 minutes. Then we're going to have a 5-minute break. Then I think Dimitri will go up. And I think 5 minutes break after that. And then Konstantin will finish up. So we have a bunch of, we have 3 talks today about memory computing in general. So what I'm going to do first is, it's titled How to Choose a Memory Computing Solution for Your Apps, but I'm going to spend a little bit more time in the beginning about what is a memory computing. I'm assuming most of you know, so I'm not going to be giving many marketing speeches here. We'll kind of quickly go technically over this and have quite a few interesting slides about some of the myth as far as what we've seen about memory computing. I've been working with this over 10 years in this technology. We'll talk about some of the product categories, and we'll finish up with some of the MSC features. So before I jump into it, when we talk about how to choose something best, I was like pretty biased. I founded this company, I work at the projects and whatnot. So we're not going to be comparing the features of product A, product B, and saying who's better, who's worse. Every vendor has a website. You can find all the comparisons right there. We have comparisons with some of the competing projects, open source and commercial. You can go to any other competing projects or companies and find the same thing. So that's not the purpose. I'm not going to be comparing X and Y's in each particular product. But what I'm going to be talking today is some of the auxiliary, thinking about how to choose which directions to concentrate, which are some of the features without comparing implementation are important for you. So, what is a memory computing? And probably, most of you probably have a kind of, subconscious understanding of that, right? You move stuff from RAM, things go fast. Typically, that's exactly how you describe that. Here's this definition over here. So, if you want to get down technically, memory computing is a kind of technology that basically uses high-performance distributed memory systems for compute and transact on large data sets in real time, orders of magnitude faster than it's possible with traditional flash and disk-based storage. So, almost every word here is kind of important. We're talking about a high-performance distributed RAM. Well, high-performance goes without saying. RAM is pretty much high-performance year after year or more. Why are we talking about distribution? It's kind of an interesting point. We talk about distributed memory because typically, even today, the single server doesn't have enough RAM to do anything interesting. So most of the systems, most of the in-memory system, historically and today, have been distributed in nature. It's kind of an interesting fact that in-memory goes with distribution hand in hand. In fact, I do believe that modern in-memory systems are probably one of the most advanced distributed systems in existence. Just to give you an example, literally 6 years ago, our system was running in production. I'm talking about GridGain and Apache 9, and over 2,000 nodes in the transaction cluster. I would challenge you to find in many other systems with 2,000 nodes in a fully transactional cluster in the financial real-time systems that can do that. And for in-memory systems, it's necessity. It's not that we're bragging about it, we do it for some reason. It's necessity. Typically, a single server doesn't have enough RAM. We have to cluster very effectively with a lot of brains behind it to really combine RAM from multiple clusters. We're talking about the transact and compute. We'll talk about this, but that's a very important point. We're not talking about only a computational thing, or basically data storage. We're talking about both data storage and processing in the memory system. It's very important because there's a lot of drive in convergent storage systems where we're not only storing data in something, but we're also processing data in the same place where we store data. But most importantly, if there's anything you want to remember about memory computing, it's speed. Nothing else matters. We're only using the memory computing for one fundamental reason, to get speed and performance. Nothing else can give you orders of magnitude performance. Think about this. It's not 2 times faster, 3 times, 5 times. We're talking about hundreds and thousands times faster compared to flash and disk storage. So that's the key. I always like to give you a historical kind of walk back. And you know, why I do believe, not only me by the way, you talk to any board analyst, they'll tell the same story, that memory computing is a paradigm shift. Think about historically, very quickly, 50s, right? Before 50s, in the late 40s, in the early 50s, we didn't have any external storage. You type the program, whatever the, pull the switches from the computers, and it goes in the RAM, you power off, program is gone. So there was a very radical idea in the early 50s, what about external storage? So Remington, by the way, out of all companies, if you're hunting Remington, basically it's a weapons manufacturer, but back then they developed the first magnetic tape device for storing data outside of computers. That's where we started the era of external storage. And then fast forward 60s and let's say late 60s, early 70s, disks become a big deal. And IBM 340 systems came around a lot early 70s, and that actually revolutionized the whole data storage, because all of a sudden we got a blazingly fast disks. Back then we called them Winchesters and multiple disks in the same kind of device. But what else happened? What else happened in the mid to late 70s? The SQL revolution happened, right? There was a tectonic change in how to store data and how to process data. Disks came around and were very, affordable, relatively affordable. And SQL won the kind of, war between multiple, approaches how to process data. So we got the affordable disks, and we got a standard-based processing for the data. 2000s rolled in, the 80s was nothing happening, but end of 90s, Toshiba really, developed a nanotechnology. It took a lot of time to really, get the economics right, but somewhere by mid-2000s, flash became pretty much, default storage for a lot of devices. Look at your iPhones, look at your tablets, look at most of your iPads and tablets and all laptops. Predominantly they have today flash storage. I'm not even thinking about this. So the flash is there the same. Somewhere around 2010, give or take, most analysts believe we entered the era of in-memory computing. And that's kind of interesting. There are multiple reasons for that transition. We can probably have spend another hour talking about it, but I do believe the fundamental two reasons: the economics and demand. The economics of 64-bit CPUs became available, and 64-bit CPUs allow you to address a lot of RAM in single blocks. The price of RAM also dropped down. It's dropping down 30% year over year. So around that time, all of a sudden, the traditional RAM became available. But also the demand of things, obviously all very big data, that's growing. Everybody needs to process a lot of data right now in real time. So in-memory was, in the focal point of that. What also happened in the same time, around the 2010, give or take, is the NoSQL revolution, right? All of a sudden, we kind of realized that the majority of the data we're generating today will be unstructured, and therefore the world of mixed structured and unstructured data is upon us. That's why I do believe, and not only me, and basically, I'll give you one more idea, that in-memory computing, as an evolutionary point, it is also the last frontier of the data technology, data storage technology. Now, it may sound a little bit, rough. Think about this. Where else can you store data that will be faster? Think about the transition from 50s to today. We store from magnetic tapes, to magnetic disks, spinning vacuum and disks, right, in the flash, no spinning, no mechanical devices. We went from flash to the DRAM. Where else? We can put it on the CPU cache, but that's very small, and only about 2 times faster than DDR4. Think about this. There is nowhere else to put the data from a high-level perspective in the current architecture of computers to make it faster or closer to application. So that's why a lot of people think that flash is the traditional point naturally. But the byte addressable storage, which is today the DRAM, but obviously there's new types of RAM coming up, both hybrid, DDR and flash, but byte addressable storage on the motherboard, on the memory controller, is the fundamental last frontier where we're going to store our data going forward. Pretty cool thing. I think Gartner has a very nice way of saying that basically RAM is new disk and disk is new tape. Most of the analysts predicted we're going to use disk only for the backup. Like we use today the tapes for long storage backups. Disks are rapidly becoming a backup device. Another take on this, and think about this, I'm giving you kind of different directions, different angles to look at the memory. Another way to look at memory and why understanding why all of a sudden memory or memory computing can be so fast is this. Not only memory is fast, right? Memory is fast, everybody kind of naturally understands this, but where does the performance, application performance comes from? This is a pretty good, indication of that. Think about the disk-first architecture. Now, you always keep saying about in memory, disk-first, memory first. Memory systems are never memory only. There's always a disk somewhere, a flash, a spinning disk, or backup, not vulnerability. But think about the disk-first architecture. What's happening in disk architecture? Imagine you have an application that needs to have access to a piece of data that's on the disk. What happens? The application calls the operating system calls the I/O subsystem. I/O subsystem makes a call to a I/O controller, and then I/O controller makes the call to a device. Device have a seek time, you found the block, then what? And then you basically have to move this block all the chain, up the chain, all the way back to application. Application has to demarshal this block from bytes to the object, and whatever. You got the object all the way chain back to device, and all the way to device and all the way back. Right? Pretty long. Now think about this. What happens when you have a data in RAM? About the only thing happens is a pointer arithmetic. You just point to a different set, different location in RAM, and most importantly, you don't do anything at all, and most importantly, say it twice, you don't have any demarcating happening, which is typically the biggest deal. It's right there in exactly the format you need. This is the difference, this is the fundamental difference between basically having data on the disk, on a flash somewhere, which is essentially the block level device, and versus having your data right there in RAM, in the same space where your application is. This is the fundamental reason you get those 2, 3, sometimes 4 orders of magnitude of performance increase when you basically go into memory computing. Let me talk about some of the myths of memory computing. The first one, absolutely too expensive. Every time we're on an Apache Ignite project introducing somebody or in a GridGain company, almost immediate reactions, God damn, it's too expensive. It's probably a myth by now. Think about this. Yes, RAM is still relatively more expensive than a flash device, given the same capacity. But think about this. I have it on the slide, but I always keep asking the audience when I basically pose the question, how do you think a terabyte of RAM costs today? You obviously can see it there, but you'll be surprised if I talk to an audience and ask, terabyte of RAM, $250,000. About 10, 20 hands in the audience. And that's roughly 10 times wrong. The terabyte of RAM today, I'm talking about the full cluster. I'm not talking about just the RAM chips. I'm talking about the entire cluster. Let's say 10 blades. Each blade has, a 100 gigabyte of RAM. The power of the network and the cage and everything else is about 20, 25K today. Now think about this. A terabyte of DDR3 with all the processing capacity, all the disk, all the power, everything else, 20K. Just to give you a perspective, a number of years ago, I think 2 or 3 years ago, maybe 4 years ago, the entire working set of Twitter, which is the all global tweets for a week, was about 7 terabytes. Now think about this, for the price of a decent Tesla, you can buy enough RAM and processing capacity to have literally a sub-second SLA on any analytics on the entire Twitter working set. The economics are there. Yes, it's not free. I always keep saying that spinning disks are literally and figuratively free today. You can get whatever. Flash a little bit more expensive. DRAM is still relatively a little bit more expensive. But in the larger terms, the too expensive kind of myth is no longer true. It's literally a myth. And obviously we have a new price of new types of memory coming up. If you guys talk to the Shiva, Micron, and any of those guys who are dealing with the new types of memory, there is a lot of memory technologies coming up, anywhere from Intel to DX1 to a variety of different types of memory, all trying to optimize cost to performance ratio. So the price of RAM will be going dramatically down and down and down. We're going to have new types of RAM, fully compatible with DDR3, DDR4 specs, but with a little bit different performance characteristics. If you don't need the extra fast memory, you can pay a lot less, literally this year or next year too. Not durable. That's another basically a interesting myth that all of us thinking, oh my God, it's a RAM, so if I unplug the computer, it's gone. Technically, unless you use non-volatile RAM, which is available today, by the way, but not really supported by software, But technically, you're right. If you unplug the DDR3 stick from the power, it loses the power. It loses the content. The point is that most any even rudimentary in-memory computing system, let alone something like Apache Ignite, which is extremely advanced in a sense, has a lot of durability and persistence built in. You can configure as much as you like, of durability options in your products and the projects. You can basically keep the copy of the same data in multiple nodes. You can synchronously, always synchronously flush into the disk, different types of storage, flash, disk, databases. You can do whatever you want. You can actually make a memory computing system as durable as traditional disk-based database. You're not going to get much performance because of that, because you're basically going to reduce itself into the disk-based systems. But you have all these extremes. What we do find a lot in our use cases, that there's plenty of use cases in our actual customers where lots of data sets don't have to be persistent at all. They can be completely lost in the event of disaster or something, and they can be recreated. A lot of financial stuff is like this. Obviously, keep transactions on disk and whatnot, but a lot of intermediate stuff doesn't have to be. You can gain dramatic performance because of that. Flash is fast enough. Another interesting, by the way, this is, in my opinion, not really as much as a myth, but it's a kind of, it's a judgment call. And I always keep saying when we're talking to customers and talking to users, it's a very simple thing. If you're looking for a 2, 3, maybe 4 times performance increase, don't look at the memory. Buy SSD, plug it in, you get it right there. Things will go load faster. Writes will go, it's not much faster, but the reads will go much faster. If you're looking for a 10x, 100x, a 1000x performance increase, Flash will not help. It was never designed for it. It will never do it for you. The only option you have is to really go for memory computing. And the difference between, people constantly asking, who needs a 10x? Think about this. If your processing takes 30 seconds, what is 10x performance increase? 3. You're not in the real time. Think about this. Your current processing takes, half a minute. If you want to go real time, you have to be somewhere a sub-second, right? It's actually more than 10x performance increase, you have to realize. Nothing will give it to you. You can rewrite your apps in assembly. It's not going to help. You cannot buy 10x more powerful CPUs unless you spend literally tens of millions of dollars. There's nothing else available to you as an engineer, as a developer, other than basically go to in-memory processing. That can give you 10 and 100x. Sometimes we've seen, up to almost, tens of thousands of increase of performance. So Flash is fast enough sometimes. If you need a small, moderate improvement, Flash is perfect. If you need a breakout of, 10x and more, there's nothing else available. Another interesting myth about it is basically memory computing is only for caching. And actually, it's been true. If you look back in history, even like 15 years ago, predominant use case for memory computing was caching. It's very natural. Databases have caching since the day one. It's a very natural idea. I have to go to the disk and I can keep certain, frequently used elements right there in RAM. But today, caching actually it's kind of used, obviously, but because there's so many apps already have caching, in memory computing becoming really, moving away from caching, just caching, becoming a system of records, where you transact the data, where you store data. For example, projects like Apache Ignite support both transactional and non-transactional access, key value, file system in memory, full SQL support, full data grid capability, full MPP, MPI, in traditional HPC type of processing. It's a lot of algorithms, a lot of technologies you can do, a lot of use cases you can process on the same data in RAM. And the cache is just one of them. Of course you can cache. Anything can be, Redis can be used for caching, which is basically a tool comparing to some of the projects we're discussing today. So we've seen a lot of usage. Most of our usage for the last maybe 2 or 3 years has been away from cache and for a variety of different system of record use cases where people transact, run SQL, run transactions, run computations, complex distributed computations, and whatnot. So let me talk about some of the categories. So we've talked a lot about what is in memory computing, some of the myths, some of the basically accelerated use in that. So what are some of the options? Now, keep in mind, I'm not talking right now about just general marketing view of in-memory, because there's in-memory analytics, in-memory BI, and everything else. I'm just talking about a middleware. So I'm talking about in-memory middleware. I do believe there's 4 options that most of us can basically be faced. The first one is in-memory, literally in-memory options. And typically those are just a buy-in options to existing databases. You know, typical culprits will be Oracle, Microsoft servers. I think IBM DB2 has an option for some kind of in-memory optimization as well. By the way, we'll talk about each of them individually. In-memory RDBMS. You know, typical example, VolDB, MemSQL. Those are typical databases that's been either rewritten or upgraded with in-memory storage engine, but those are traditional SQL databases. Next one, in-memory data grids. This is kind of minimal bona fide developed architecture from scratch in-memory computing middleware. It's specifically designed for in-memory first. It's not a database retrofitted, it's not an option. It's from a ground-up middleware developed specifically for in-memory computing processing. Last one, memory data fabric, which is an extension of a memory data grid. It adds stuff to it and make it a little bit more strategic on what it can do. So we'll talk about each individual one of them. In-memory option, it's the first one. It's literally an option. If you guys run in Oracle, you just want to spend a couple of $100,000 more, you can go to Oracle, buy that option, enable that, and certain tables can be stored, and indexes can be stored in RAM. Things will go faster for certain use cases. The key here, it's a feature into the existing databases. There's absolutely zero integration. There is literally no need to do anything, no API changes, no code changes, no data migration required. The concept of that is extremely limited benefits. It's literally, I would never call it a memory computing option, but it exists today. But you know, literally, it's more or less just an optimization of existing database that you can basically get. But from a marketing lingo, it's there. So we'll talk briefly about that, but that's about it. So in memory databases, in memory RDBMS, this is kind of, for me, the first where it started making any kind of sense. So if you guys, for example, look at MySQL, and you want to have a MySQL with a memory storage, there's a company like MemSQL that basically did that for you. So if you want to stay with SQL, if you don't want to move anywhere, if you want to just basically just have a SQL, nothing else, just SQL, but you want to have a different database with memory storage, there are a couple of companies, VolDB, MemSQL, and pretty cool projects you guys can look at. What's the downside? Well, downside is very massive. You have to move to a different database. So if any of you working in an organization, try to replace Oracle with something else. Try to replace DB2 or Microsoft SQL. It's a pretty big effing deal to replace it. It could be multiple years of project. So this is the biggest kind of concern. You're not getting a lot in return because you're just getting the same database that can work faster in certain use cases, but you have to migrate the entire data, not the entire back office application potentially, if they're not compatible with database. Another very significant problem with in-memory databases, and actually removing memory to talk about databases, is scalability. SQL doesn't scale. It was never designed for it. It doesn't scale, in a true scale. You can shard it, but it's a very primitive way. You can basically say, look, portion of my data here, portion of my data is there. But it's a very primitive way. SQL doesn't scale. It doesn't scale because of joins. If your tables are pretty big and joins are pretty big, you basically face the same fundamental problem of key explosion. You have to exchange all the keys everywhere. So yeah, if your tables are pretty small, everything works. If your tables grow into the millions, you can forget about distributed joins. You can kill either network or the RAM with both boxes. So one of the problems with the SQL databases, doesn't matter, disk or memory, they do not scale. And fundamentally, take a look at the Oracle. Anybody using Oracle racks or multiple partition Oracle databases? That's the reason those typical racks can go in 2 or 3 partitions, but not 200. If you've never seen a database that can go scale out to 200 or 300 nodes, it'll be pretty nice because you can utilize parallelization, but you can't in SQL. SQL doesn't scale.
But that has nothing to do with SQL. It's an implementation artifact. We've been implementing SQL in a stupid and naive way for 30, 40 years. That's not inherent in the relational model, and it's not inherent in the language. SQL is a language, and it's an interface. It's not the engine.
I agree with you. So that's a good point. So we're talking about SQL implementation, not SQL the language.
Fair enough.
Yeah. So, but guess what? If Oracle cannot make it work effectively, the problem is not trivial. Because there are quite a few companies that are trying to make it. We, for example, do distributed SQL, but we're bound with the same limitations as well. Anyways, in-memory data grids, this is the area where it starts a little bit become more interesting, because the in-memory data grids is the first kind of what I call the bona fide in-memory middleware. It was designed from scratch to be specific for in-memory processing. The big plus of in-memory data grids is that they optimize for ultimate performance. And they provide all the specific APIs and paradigms to do effective in-memory processing. It has, again, a key value access to the RAM, which is pretty close to the byte reversibility. It typically has some transactions. It may or may not have some SQL capabilities, but it is the systems that are designed from scratch to be a perfect fit for memory computing. The typical negative side of that is that all of a sudden at this point, it will require a potentially significant integration effort. Because the difference between the key value in proprietary data grid APIs, between that and SQL, for example, is pretty significant. Some of the data grids may support certainly, a subset of SQL or some other, query language, but the integration effort is no longer just an hour or a day. It could be weeks and it could be months sometimes. So this is the major, kind of negative side, if you will, of data grids and essential data fabrics as well. They do require a substantial integration effort. In return, you can get those 10, 100, 1,000x performance increase from your applications. And finally, memory data fabric. So the memory data fabrics are built on top of data grids. And the difference there, they provide more functionality, more capabilities than just data grids. Typical data fabrics would have a full SQL support, a full streaming complex event processing. They would have things like file system integration and whatnot, or Hadoop integration, or Spark integration, and a variety of different things. So fabrics really treat in-memory as kind of a strategic layer of performance. It's based on RAM. You can put a lot of data into it, and you can do whatever practically you want with this data, right? You load up in RAM across multiple computers. You can do key value access. You can do SQL. You can do transactions, non-transactions. You can do MPP, processing. You can do traditional, high-performance parallelization. You can do, Spark integrations, Hadoop, and stuff like this. So whenever we talk about data fabrics, and I'm a little bit biased here because the Apache Ignite project, which I'm involved with, is in-memory data fabric. The idea is there that we just move away from just the grid use case and treat RAM as a strategic storage layer with all the different types of processing you can do on top of it. So this is the kind of summary of what, 4 options. And those, again, despite the fact that I'm kind of, being negative on the first one, it's always the judgment call you have to make. What really works for you, for your project. Sometimes, database options is perfectly fine. It's not often, but I've seen that it's working. Obviously, combinations like OLDB, MemSQL, they're pretty successful. They do something right. There's plenty of customers for that. We also basically see, obviously, a lot of traction with data grids and data fabrics. But I'm not going to be pregnant here. I have a last slide here, and if I can borrow 5 more minutes. Some of the key features on data grids and fabrics. And I'm not going to be telling you who is doing the better and worse. You guys can decide for yourself. But some of the interesting capabilities you have to be able to look at. First of all, scale out and scale up. Basically, horizontal and vertical scale. It's very, very important because depending on what your application is doing, you sometimes want to have a clear horizontal scale out to tens and sometimes hundreds of nodes. But sometimes you want to have your app or your middleware supporting a vertical scale. What if you have one of those Fujitsu boxes with 5 terabyte of RAM on it?
64 terabytes.
Or 64 terabytes, yeah. There's plenty of computers available today with that architecture, with that kind of architecture. You have to be able to work on that box as well. So it may sound obvious, right? Why wouldn't you, right? But believe me, there is a fundamental difference in how you treat, a horizontal scale system or a verticalized scale system. There's one example on the Fujitsu box. There is no network overhead. Everything is instantaneous in this box. So you have to really test this and really have your vendor or the project you guys using to really tell you if it's working or not. We learned pretty hard way, but it's absolutely not automatic. We thought it is. It's far away from being automatic. If you work in one environment, would you work in this environment? you have to design your system, you have to fix a lot of stuff to make it work. So that's an important consideration to really see if your middleware of choice can do that. When it comes to memory data grids, things like fault tolerance, things like transaction, things like SQL support, those are pretty obvious, but in most of the projects do support these features in some way, shape, or form. But let me give you an example about SQL. Always ask what kind of SQL is supported. There's a pretty big deal between the full SQL 99 support, where your transition to this system can be very painless, versus some kind of sub-language that looks like SQL with a long, long list of exceptions. If you take your Oracle SQL, you're going to spend days and days and days really trying to bend it over to make it work with some kind of proprietary language. So supporting, for example, standard SQL 99 or something like this can significantly shorten any kind of transition, any kind of integration work. Cross-language interrupt. I mean, most of our stuff today is written in a bunch of languages, right? Your front-end JavaScript, your back-end Java, Scala, C++, your .NET infrastructure. I don't think you can find middleware that works everywhere, but the projects that actually have either clients in multiple languages. Look at MongoDB. Why it's so wonderful for use cases? It's the ecosystem of drivers for every goddamn imaginable language that exists on the earth, right? That's the beauty of the Mongo. You can basically use it everywhere. So it applies to any project. It applies to in-memory computing systems. Your backend can be .NET, it can be C++ straight, it can be Java, it can be Scala. Your front-ends can be Node.js, can be REST. Always look out what's available. Because if it's not available, you're in a world of pain to basically develop yourself. And it sometimes can be pretty hard. When it comes to compute grids, look at what's available. And typically, people just make it some kind of runnable interface available to you. But it's not enough. Computational grids just as complex as data grids in terms of computational semantics. Things like all these abbreviations like MBP, MBI, HPC. If you guys are familiar, you recognize them. All these different types of processing. How do you fail over? How do you roll back? How do you parallelize? How do you balance? A variety of different questions. Obviously, if you guys into the kind of enterprise usage, things like security, but it goes without saying, management, manageability. Look at it if you need it. Last but not the least, things like Spark and Hadoop. It's hard to find a project today that's not touched by Hadoop ecosystem or Spark ecosystem somewhere. You guys doing something with it. It's nice when middleware provides support for that, because those are very key elements in typical big data ecosystems, and you have to have some level of integrations with it. I'm out of time, so this is my last slide. I'm not going to be taking questions, but I'm going to be around here because we're out of time for sure. And I think Dimitri will be next, but we'll take a 5-minute break or not? All right, 5-minute break, and then next one's coming up. Thank you, guys.